Welcome. In this session, we will be looking at a case study involving production planning. So far, we have studied 5 meta-heuristic techniques and we have also discussed how to handle constraints. Right? As part of this case study, we will be looking at the production planning problem. The production planning problem consists of k raw materials, and using those raw materials, we can produce different types of products. Right? So, for the conversion of this raw material into a particular product, we process that raw material, right. So, there are various types of processes. So, this is process 1, process 2, process 3 and all the way up to we have J processes. So, k raw materials when processed can give us product, right. So, some of these processes can produce identical product, right. So, for example, process 3 and process 4, if you see, it produces product 3. So, that is possible, right. For each of this process, we know the production cost, right, and investment cost for a specified level, right. So, for example, if we produce L11, right, the investment cost is V11 and the production cost is C11. So, similarly, we have different levels at which we know the production and investment cost. So, for example, let us say for a particular process, we know that the production cost is known at, so let us say level L, level M, level H, right. So, it is like if we produce 50 kg per day, we know that this is the production cost. If we produce, let us say 125 kgs per day, the CM denotes its production cost. If we produce, let us say 300 kgs per day, the CH denotes the production cost. So, the production costs are known at these 3 levels, level 1, level 2, level 3, right. So, that is what this level corresponds over here, level 1, level 2, level 3 and all the way up to it can have any number of levels. Similarly, at this production level, we also know the investment cost, right. So, IL is the investment cost to produce 50 kgs per day, IM is the investment cost to produce 125 kgs per day and IH is the investment cost to produce 300 kgs per day. So, this is known. So, now if we have to find out the production cost, let us say at 75, right. So, we know the production cost at L at 50 and we know the production cost at 125. So, the production cost at 75 is a linear function, right. So, that is part of the problem definition. We are not assuming it, right. So, as part of the problem definition that has been given. So, in that case we know this point. So, if we call this point as let us say x1, x2, right. So, CL is nothing but y1 and CM is nothing but y2, right. So, we know x1 y1, we know x2 y2 and if we are told that it is a linear function between x1 and x2, we can calculate the production cost for any value between 50 and 125, right. So, similarly, between M and H, the production cost is linear. Just like production cost, the investment cost is also linear, but the slope and intercept are different as shown in the figure. So, these two put together, right, is a piecewise linear function. It is linear in this range and it is linear in this range. So, similarly, for investment cost, it is linear in this range and it is linear in this range. So, this is a piecewise linear function. So, here if we see, right, so if we have 3 levels, right, L, M and H, right, and if we have J process, here we have shown that each process can have different number of levels, right. To simplify, let us say the number of processes that we have is let us say 10 and for each process we know the production and investment cost, let us say at 3 levels L, M, H, right. So, here for every process if you see we will have 4 lines, right, line A, line B, line C and line D, right. So, if we have 10 processes, we are going to have 10 into 4, 40 such lines. So, this we have seen that there are k type of raw materials, J processes and which can produce T different products, right. So, a product can be produced by more than one process, that is what we showed you for this product 3, right. So, production cost and investment cost are known at different production capacity levels, right. So, in this figure they were known at L, M and H, right. Cost between successive known levels are a linear function of the quantity that is produced, right. So, this also we have discussed that between L and M it is a linear function, between M and H it is a linear function. Should there be some other level between H and that particular level, again the function is linear, right. So, here our job is to find out, right, which of the products need to be produced, right. So, for each product we know that there are different types of processes which we can use to produce it, and depending upon how much we are producing, right, the production cost and the investment cost is going to be different, right. So, here there is no compulsion that we need to produce all the product, right. So, not all the products need to be produced, right. We are going to produce only those products which are profitable. So, here the constraint is that if a product is produced, right, the production below the minimum level. So, the minimum level in this figure is L, right. So, if we say, let us say L is 50, M is let us say 125 and H is let us say 300. Let us say this is for process 1. So, if we decide to produce from P1, right, we can choose not to produce anything from P1, 0 is allowed, right, but if it is greater than 0, then it has to be definitely greater than 50 and less than 300. Here if you see this figure, right, so we do not have a procedure to calculate the production which is greater than 0 but less than L, right. We have a procedure to calculate the cost between L and H, right, but we do not have a procedure which can help us to determine the cost which is greater than 0 but less than L, right. So, if produced, this is important, if produced, it is not necessary that we produce. If we decide to produce, then we need to make sure that the production is greater than or equal to 50 and less than equal to 300, right. So, that is a unique feature about this problem. Most of the problems that you would find in conventional optimization textbooks, mostly they would have problems which will give you domain as let us say between 0 to 100 or let us say between 20 to 100, right. Here we have a domain wherein 0 is permissible, right. So, 0 is permissible and any value greater than 50 and less than 300 is permissible. So, x is between 50 and 300, right, and x can be also 0, right, but x cannot be let us say 42 because 42 is greater than 0 but it is less than 50. So, the objective here is to maximize the profit. Let us say the selling price of product 1 is 5 rupees per kg, right. So, if we decide to produce 10 kgs, then the revenue that we will earn is 5 into 10, right. So, that selling price is known. What we need to decide is how much to produce. Once we decide how much to produce, we can calculate what would be the revenue, right. So, that is the total selling price, right, and as we have discussed, depending upon how much I choose to produce. So, let us say it is 50 here, this is 125 and this is 300. Let us say if we decide to produce 200, right. So, then this is the production cost from this particular process, right. So, the sum total of all the production costs. So, we may even choose to produce from process 1, process 4 and let us say process J, right. So, the total production cost is production cost incurred here, production cost incurred here and the production cost incurred here. Similarly, the total revenue which is earned is the revenue earned by selling product 1, revenue earned by selling product 3, right, because process 4 produces product 3 and the revenue incurred by selling product I. Right. So, the profit is given by the difference between the total selling price and the production cost, right. So, here if you think about the problem, if there are no constraints, right, then one may choose to employ all the processes, right, all the processes and produce the maximum quantity that will fetch the maximum amount of profit, right. So, but here we have two constraints, the budget to establish this plant, right. So, right now these are our options, right, it is not like this plant is already existing, right. So, we need to choose what to produce. Depending upon we decide to produce, we will employ appropriate process and establishing a process itself is going to incur us a cost, that cost is nothing but investment, right. So, here if we decide to produce 200, then the production cost is what we have shown here, right. If we decide to produce 200, then the investment cost is to found from this line, this is going to be our investment cost. So, here the y axis is cost, right, and the x axis is the production quantity. Depending upon which are the processes that we select, we can also determine what is the total investment that is required, right. So, the total investment that is required should be less than or equal to the budget available. So, it is more like let us say 500 rupees are available and you are going to go and shop something. So, whatever you decide to shop should be less than or equal to 500, right. So, that is what this constraint is there. Similarly, not all of these raw materials are available in abundance, right. So, limited amount of raw materials are only available. Let us say we decide to produce 100 kgs from process 2. So, the amount of raw material that would be required to produce this quantity should be less than or equal to what is available. So, let us say if only 50 kgs are available of raw material 2 and producing 100 kgs of the product 2 requires let us say 170 kgs of raw material 2, right, then we cannot even produce 100 kgs of product 2 from process 2. So, whatever the total amount of raw material is required should be less than equal to what we have over here, right. So, that is another constraint. So, these two are the explicit constraints that we have, right, budget constraint and raw material constraint. Again, raw material constraint is a type of constraint. We can have one constraint on raw material 1 one constraint on raw material 2, one constraint of raw material 3. If raw material 4 is available in unlimited quantity, then we will not have a constraint on raw material 4, right. So, depending upon how many raw materials we have, right, and their availability, we may have that many constraints, right. And here you need to remember that the problem does not require that all products be produced, right. We are given the choice to produce the products that are most profitable. So, this is the definition of production planning problem, right. So, for additional details you can look into this reference, right. So, in this reference they use mathematical programming approach to solve this problem. If you remember, for this course we had classified optimization techniques into two categories, right. One is meta-heuristic techniques and the other one is mathematical programming techniques, right. So, since we have only looked into meta-heuristic techniques as of now, right, we will see how to solve this problem, right, with the help of meta-heuristic techniques. The solution procedure that we are going to discuss in this lecture is not given in that paper, but the problem definition is exactly the same that was handled in this research work. So, this case study is reported in that research work, right. So, here they have 24 products, right. So, as of now in this slide we have shown you only 8 products. So, T1 to T8 are the products, right. So, T1 can be produced by P1, P2 and P3. All the 3 processes are capable of producing T1, right. So, we may choose to produce the product T1 from P1 as well as P2 as well as P3, right. So, as of now there is no requirement that a product has to be produced from only one process, right. So, all these 3 processes are capable of producing it. If required, we can use all the 3 processes. So, these are the capacity levels, right, at which the production cost and investment costs are known, right. So, for units of product we can take it as tons, right. So, if we decide to produce 70 tons per year, we know the production cost and the investment cost. If we decide to produce 135 tons per year, the production cost and the investment cost is known, right. And if we decide to produce 270 tons per year, we know the production cost and the investment cost, right. So, here if we produce 70 tons per year, right, the production cost is 50.7 monetary units per unit of product, right. So, if we decide to produce let us say 135, the production cost is 90.1. If we produce 270, the production cost is 170.7. Remember, a common misconception is that we need to decide between 70, 135 and 270. So, that is not correct, right. We can still choose to produce anything that is 70 or greater than 70, but less than or equal to 270. Right. So, then in that case how do we determine the production cost is using that piecewise linear function which we had discussed, right. So, if it is 70, so 70 is this 50.7 on the y axis, right. So, this is one data point and the other data point is 135, right, and 90.1. If we decide to produce something which is greater than or equal to 70 and less than or equal to 135, we can use this linear line, right. So, this point is known. For this point the production cost is 90.1, right. So, this is also known. So, in between 70 and 135 we can still estimate the production cost, right. Similarly, between 135 and 270 we know the production cost is 90 and 170.7. So, similarly the investment cost is given, right. So, if we decide to produce 70, the investment cost is 55, right. So, 55 monetary units per unit of product, right. If we decide to produce 135, the investment cost is 81.1. If we decide to produce 270, the investment cost is 131. So, if we decide to produce anything between 135 to 270, the investment cost can be calculated by the points connecting 135, 81.1 and 270, 131.6. Right. So, there are 3 different types of raw material which are required, right. So, process 1 to process 18 do not require raw material 2 and raw material 3, right, only raw material 1 is required. So, the amount of raw material required is 0.948. So, if we decide to produce 1 unit of product 1 from process 1, we require 0.948 units of raw material 1, right. So, if we decide to produce let us say 95 over here, right, the amount required for 1 unit is 0.9546. So, the amount required for 95 would be 95 into 0.946, right. So, raw material 2 and raw material 3 are not required for any of the first 18 processes, and we also know the selling price of each of the product, right. So, product T1 for 1 unit of product T1 can be sold for 0.975 monetary units, right. So, if we decide to produce let us say 60 over here, right. So 1 unit can be sold for 0.780, for 60 units it will be 60 into 0.780, right. So the selling price and the raw materials can be directly calculated. Only for the production cost and the investment cost we need to use that piecewise linear function to determine the actual production and investment cost. So this is from product 9 to 17, right. So here if you see, raw material 1 is not required, right, and raw material 2 is not required for these processes. Raw material 2 is required for these particular processes, and none of these processes use raw material 3, right. So for example, for these processes if you see P35, P36, P37, it does not use any of these 3 raw materials, right. So that means it uses some other raw material on which we do not have any constraints, right. So here we are only considering those raw materials on which we have availability constraints, right. So this is the last section of the data, right. So here raw material 3 is required for these processes. So this is the same data which we have shown you, right. So over here we now need to decide what are the products that need to be produced, right. So we have the choice to produce the product, right. So that is why it is an optimization problem. We need to decide what are the products that we are going to produce, right, and for each product that we decide to produce, we need to select the process also. So as you have seen, so some of the products have more than one process which can produce it, right. So we need to select the process, and we also need to decide on how much quantity we are going to produce, right. So the amount of production from the processes that have been selected. Products have to be selected, processes have to be selected, and then we need to also select amount of production, right. So these are the decisions that we need to make, right, such that the profit that we obtain from whatever we decide to produce should be maximum, and whatever production plan that we come up with should require an investment which is less than the available budget, and the raw material required for the production plan should also be less than or equal to the raw material that is available. So now we have discussed this, right. So this is the problem, right. So recollect the meta heuristic techniques that we had discussed, right. So for that, first thing we need to give is lower bound, upper bound, and the fitness function, right. So now the question is, what are our decision variables, right. Only if we know our decision variables will we be able to give the lower bound and upper bound, right. So now we need to resort that what would be our decision variables, right. Whatever we have discussed here, this is what is required. So we will be discussing 2 approaches. So the first approach is the one that usually strikes us, particularly when we see these 3 things. So we will discuss what is the disadvantage of that approach, right, and then we will be using the approach with which we will be able to solve this problem. So for meta heuristic techniques to work well, right, it is necessary that we choose the decision variables carefully. We will need to select the decision variables and the constraint such that it captures the complete definition of the problem, right, and we should try to avoid excessive decision variables. So in this case, just for easier understanding, we are working with only 3 products, right, product T1, T2, T3. So product T1 can be produced from P1, P2, product T2 can be produced from process 3, process 4, process 5, product T3 can be produced from process 6, and these are the levels at which their production cost and investment costs are known. Production cost and the investment cost for process 1 are known at 5, 10 and 20, right. Similarly, the production and investment cost for process 4 are known at 2, 7 and 20. So anything above 20 is not permissible, anything below 2 is not permissible, right, but 0 is permissible. If we decide not to produce a product, that is fine, right. So there is no compulsion that we need to produce a product. So the production quantity can be 0, but it cannot be greater than 0 but less than 2. One way to approach this problem is to define 3 binary variables, right, indicating whether a product is produced or not, right. So whether T1 is produced or not, this is a decision variable, right. So any of the meta heuristic techniques that we discussed will be required to give us the values, right. So it has to give either 0 or 1, right. So this is the first section. The second section is we have another 6 binary variables, right. So for example, for this process, if I just say that T1 is required in, let us say 11 quantity, T2 is required in, let us say quantity 18, right. So if we say this is the production plan, then it is not a complete production plan. We are only saying that we want to produce 11 units and 18 units. We are not saying which of the process we will use, and depending upon the process that we use, the production cost and the investment cost would be varying, right. So we also need to make a call on the processes, right. So here again we define 6 binary variables, right, P1, P2, P3, P4, P5 and P6. So we have defined variables which are binary variables. Those variables can take only 0 or 1, right. It cannot take any value in between 0 and 1, it cannot take a value of 0.5, right. It has to be either 0 or 1, because if I say P2 is equal to 0.5, it does not help me to infer whether the process is selected or not, right. So, P1 is equal to 0, we will say that the process is not selected, P1 is equal to 1, the process is selected, right. So, if it is 0 or 1, we can decide whether the process is being used or not. So, it should not contain continuous values, right, it has to be either 0 or it has to be 1. So, again this is not sufficient, right, we also need to know what is the production quantity, right. So, since there are 6 processes, we will ask the algorithm to give 6 values which will indicate the amount that is being produced, right. So, that would be 6 variables, so right. So, here it is 3 binary variables, again 6 binary variables and 6 continuous variables, right. So, we have 15 variables, right. Out of 15 variables, 9 are binary, right, the first 3 and the next 6 are binary and the rest of the 6 are continuous variable, right. So, this binary variables, the lower and upper bound is clear, because it is a discrete decision that we need to make whether the process is used or not and the product is produced or not, right. So, those are binary variables, whereas for this continuous variables, the question is what should be the domain, right. The upper bound is clear, right. So, the upper bound cannot exceed these values 20, 22, 20, 20, 25 and 20, right. So, the upper bound is clear, that is Hj, right. So, this j indicates the jth process. So, there are 6 variables, the upper bound of the first variable is 20, the upper bound of the second variable is 22, the upper bound of the third and fourth variable are 20, the upper bound of the fifth variable is 25 and the upper bound of the sixth variable is 20, right. So, the upper bound is clear. Coming to the lower bound. So, the question is, should the lower bound be 0 as we have shown here, or the lower bound should be 5, 8, 4, 2, 10, 3. So, if we choose this as lower bound, right, then we are implicitly enforcing a constraint that every product has to be produced. So, if we consider process 2, right. So, if we declare this as the bounds, right. So, then x2 cannot take a value of 0, right. If x2 cannot take a value of 0, we are implicitly forcing that process 2 has to be used, right, which is not part of the problem definition, right. So, since the problem definition allows a process not to be used, we need to give lower bound as 0, right. So, this bound is not allowed, right. So, this is wrong. If we are enforcing this, right, then we are implicitly enforcing the constraint that every process has to produce a product which has to be between its lower and upper bound, right. So, here we are for process 2, we are enforcing, though the problem definition does not have the requirement that process 2 has to be used, if we take this as bound, then we are enforcing that constraint that process 2 should produce at least 8 and at most 22. Now, if we are, let us say if we are to use TLBO, so the lower bound is we will give 0, 0, 0 9 times, right, and then we will give again 6 another zeros, right, and the upper bound is 9 times 1, right, and then Hj, right. So, the upper bound would be 20, 22, 20, 20, 25 and 20. So, this is the lower bound and this is the upper bound, right. So, all the algorithms which we have discussed are guaranteed to give values between the lower and upper bound, right. So, for the first 9 variables, if you think about it, it will definitely give a value between 0 and 1, but there is nothing in the algorithm which will make sure that the value that it returns is an 0 or 1. So, for example, consider the teaching phase, right. So, in teaching phase when you employ that equation, you may end up with a value of 0.2, right. So, that is what is going to be fed to the fitness function, right, but a value of 0.2 for the first decision variable over here, right. So, let us say a value of 0.2 does not make any sense, it has to be 0 or 1. So, that is the first problem with this encoding. So, this is how we are coding the solution, right. So, this is called as encoding, right. The first problem is the algorithms that we discussed are for continuous variable and here we are having a binary variables, right. So, that is the first issue. So, one way to overcome that issue is we will say whatever values are returned by any of the 5 meta heuristic techniques that we discussed, right, we will round it off, right. So, if it is 0.2 we will round it to 0, if it is 0.7 we will round it to 1. So, that way we can handle that problem. So, let us look at some of the other issues, right. So, for example, consider this solution, let us say we get this from TLBO, either we get this or whatever we get for the first 9 variables we round it off, right. So then let us say this is our solution 1 1 0 1 0 1 1 1 0 and then 6 0 10 5 20 0, right. So this is what we will get from the algorithm. So what does this mean, right. So this solution means that product T1 and T2 are produced, right, because here we have 1, right. Product T3 is not produced, right. So since product T3 is not produced, P6 has to be 0. Here if you see there is only one process. So if this is 0, this one has to be 0, and in this case it happens to be 0. So if T3 is 0, P6 is 0, means that process 6 is not selected. So if process 6 is not selected, the quantity that we produce from process 6 should be 0, right. So over here also we have a 0, right. So for product 3 it is consistent. Let us check for product 1, right. So for product 1 we are using the process 1, right. Process 2 we are saying that we will not select process 2, right. So since we are selecting process 1, we need to also know how much we are producing. So this is let us say 6, right. So process 2 we are not using, right. So 0, so x2 is also 0, which is consistent. And if we talk about product 2, right, P3, P4, P5, right. So all of the processes are selected. So product 2 is being produced from process 3, from process 4, from process 5, all the 3 process, and all of these are non-zero values 10, 5, 20, right. So in this case what the encoding that we chose is consistent, right. So what information that we derive from here consistent with this, and these two information are consistent with this, right. So that is why we have termed this solution as it is consistent, right. So what this solution basically tells us that product T1 and product T2 are produced. We are using process 1 for product 1, right, we are not using process 2, and for product 2 we are using all the 3 processes, right, P3, P4, P5, and this is the production quantity, right, 6, 10, 5, 20, right. So if this happens, if we get a solution like this, right, we can decode that solution, right. So now this is the decoded solution. So whatever meta-heuristic techniques we have discussed, they will give a solution like this, what we have mentioned over here. So this is the solution that it will return, right, and that solution we can decode, right. So now we know the decoded solution. So now we can go and calculate what is the production cost, what is the investment cost, what is the profit, whether we are satisfying the raw material constraint and all those things, right. So but assume had we got something like this, right. So remember our lower bound was 0 9 times, 1, 2, 3, 4, 5, 6, 7, 8, 9. Our upper bound was 1, for all of this the upper bound was 1, and the lower bound for these 6 were also 0. The upper bound over here was so 20, 22, 2 times 20, 25 and 20, right. So this is the lower bound, this is the upper bound. So it is perfectly possible that we get a solution like this as given over here, right. So this is the decision variable which we obtain from any of the meta-heuristic techniques, right. So now let us see what does this solution indicate, right. So this solution indicates that process P2 is not used because it is 0, right. So that was our encoding scheme. If it is 0, it means we are not using that, right. Whereas look at x2, right. x2, what does it denote? How much we are producing from process 2, which is 8, right. So here this part of the information is saying that we are not using process 2, whereas this part of the information is saying that we are using process 2 and producing 8 units. So that is inconsistent. What we are getting from here and what we are getting from here are inconsistent, right. Now it becomes a problem as to which one is correct. Should we make this x2 as 0, right, because P2 is 0, or we should make P2 as 1 because x2 is 8. Only then this information would become consistent and we will be able to calculate the production cost, right. If we select this encoding scheme, so we may end up with this inconsistency, right. So a couple of more example for inconsistent solution. Again this is a solution that we can get from meta-heuristic technique. Let us say this is the solution which we get from meta-heuristic technique, and the first 9 values were not binary, we rounded it off so that we get binary, right. So over here if we see, this part says that T2 is not produced, right, whereas P4 is 1, right. So the algorithm does not know that we are solving a production planning problem, and that if T2 is 0, then P4 has to be 0, the algorithm does not know. For the algorithm, these are decision variables, right. So, nothing in the algorithm says that the second variable and the 7th variable should be consistent, right. So, the algorithm will give values between the lower and upper bounds, that is what we have discussed, right. If it is to give values only between the lower and upper bounds, we may end up in situations like this, wherein the first part of the information is not consistent with the second part, right. And over here if you see x3, x4, x5 as we discussed indicate the production from process 3, process 4 and process 5, right. So, here we are saying T2 is not produced, right, but the process 4 is active, process 3 and process 5 are not active. Again we have a complication here, right, that we are saying process 3 is not active, but we are saying we are producing 10 from process 3. Process 5 we are saying it is not active, but we are producing 20 from process 5, right. So, again it leads to an inconsistent solution. So, similarly this is another example of an inconsistent solution, right. Here the first part of the information tells that we can produce T3, but P6 is 0 and X6 is 10. So, now the question is, should we make this as 1 or we need to trust that this 0 is correct and make this as 0 and make this as 0, right. That call needs to be taken. So, that is the problem with this approach. Remember, the problem does not tell us what are the decision variables, it is we who are to identify what are the decision variables, right. So, if we decide to choose the decision variables in this pattern, right, then we may end up in situations wherein the solution that we are getting from the algorithm itself is not consistent, right. So, now we can either go ahead with this scheme, right, and as soon as we get this solution we make modifications to the solution and then do something and calculate the cost, or the question is there a better approach to select the decision variables, right. So, so far whatever we discussed was approach 1. So, now let us look at approach 2. So, in approach 2 what we are saying is that we will have only j decision variables. The first variable will denote how much we are producing from process 1, the second variable will tell us how much we are producing from process 2, third variable will tell us how much we are producing from process 3, fourth variable will tell us how much we are producing from process 4 and so on, right. So, we are saying that now we will define only j variables, right. So, for this example we are saying that we will only define x1, x2, x3, x4, x5, x6. We will define only 6 variables, right. We are not making an explicit call whether we are producing product 1 or not, whether we are producing product 2 or not, whether we are producing product 3 or not, right. And similarly we are not making an explicit call whether we are using process 1, whether we are using process 2, process 3, process 4, process 5 and process 6. So, the first 9 variables which you saw, right, that we have removed, right. We are only sticking with the last 6 decision variables, right. So, the question is, if I know these values, can I construct additional information which is required. So, for these 6 variables the lower bound will be 0. We have discussed couple of times why the lower bound has to be 0 and not Lj, right. It should not be Lj, the lower bound has to be 0, right, because the problem definition does not require us to use all the processes, right. So, to capture the feature that we can choose not to produce from a process is possible with this encoding only if we take the lower bound as 0 and Hj is the upper bound, right. So, this is the upper bound of the 6 decision variable, right. So, if we give to the algorithm 0, 0, 0, 0, 0, 0 as the lower bound and if we give this as the upper bound, right, 20, 22, 20, 20, 25 and 20. Let us say we give this lower bound, we this give upper bound. So, between this lower and upper bound it will generate let us say n random solutions, right. So, let us say one of the solution looks like this 12, 9, 5, 18, 14 and 7. Now, the question is this sufficient amount of information for the problem? Remember when we defined the problem we said we need to decide whether a product is produced or not, which is the process that we are going to use and how much we are going to produce. So, in the previous approach the answer to these questions we put it explicitly. The first part will tell whether a product is produced or not, the second part will tell whether a particular process is used or not and the third part will tell us how much we are producing from that particular process, right. So, with that encoding we saw that we may end up with inconsistent solutions, right. So, rather than getting an inconsistent solution from an algorithm and then working it out, right now we are seeing whether if we choose only the last 6, that how much is being produced from each process. With that information can we answer all the 3 questions, right. So, the answer to that is yes, right. So, here if we see x1 is 12, right. So, x1 is 12 means we are using process 1, right. x2 is 9, right, which means we are using process 2, right. All these are non-zero values, which means we are using all the processes, right. So, process 1, process 2 is used, process 3, process 4, process 5 is used, process 6 is used. So, how much we are producing it is explicitly obtained from the algorithm itself, right. Whether we are using a particular process or not can be derived from this information. So, let us say instead of 14 this had been 0, let us say, right. So, this is not over there, this is 0. So, which means we are using P1, P2 to produce product 1, we are using P3, P4 to produce product 2, we are using P6 to produce product 3, and P5 is not used had it been 0, right. So, now let us see that for this how much product we have produced, right. So, for example, T1, so T1 is produced by P1 and P2, so we can add this 12 and 9, right. So, that means that we produce 21 units of T1. For T2 we need to add all that we obtain from process 3, process 4, process 5, that works out to be 37, and for product 3 we use process 6, right, because this is non-zero, 7 is non-zero and the total amount produced is 7, right. So, let us say if this was 0, if this was 0, right. So, that means P1 would get away, right, and this 12 would be 0, right. So, we will have only 9, so this 5 would go away, so process 3 would go away, right. So, this is process 1, process 2, process 3, process 4, process 5 and process 6. So, this 5 would go away. So, this will be 18 plus 14, this will be 32 and this stays, right. Had this been also been 0, right. So, then this will be 0, right, process 6 is not used, right, and the amount of T3 produced is 0, right. So, here in the second approach we are saying that it is sufficient if the algorithm tells us how much is to be produced from each process. The algorithm does not need to explicitly decide whether we are producing a particular product or not, and it does not explicitly need to decide whether we are using a particular process or not, right. So, that information can be derived by knowing how much we are producing from each process, right. So, let us consider approach 1 and approach 2, right. So, let us say these are binary variables and these are continuous variable, right. Let us say we had T products, right, and we have P processes, right. In that case the number of binary variable that we had was T plus P. First T will tell whether a product is produced or not, the second P will tell whether a process is used or not, and again we had P continuous variables, right, which tells us how much we are producing from each process, right. Whereas in this second approach if we see, and despite using this many variables, this was giving us inconsistent. So, this can give us an inconsistent solution which we need to again sort it out before we can evaluate the fitness of that solution, right. Whereas in the approach 2 if we see, we have not used any binary variable, right. So, the binary variable is 0, right, and we need to use only P continuous variable, right, and this information what we get from here is actually consistent, right. By the second approach we will be getting consistent solution. Remember, we are using the word consistent and not feasible, right. Feasible is one which satisfies all the constraints, right. Here we are using the terminology consistent to understand that there is no conflicting information within the solution given by the meta heuristic techniques, right. So, in approach 1 we were using large number of variables, but still the information that we may get from the algorithm was inconsistent, whereas in the second approach we are not using any binary variables, which is in a way good, right, because the algorithm itself is not designed for binary variables, right. So, we are not using binary variables, we are only using continuous variables, and the information which we get from the algorithm will be consistent. So, now we will choose this approach, right. So, our decision variables are going to be how much we are producing from each process. So, that is what the algorithm is going to tell us, and that is what the algorithm needs, lower bound and the upper bound, to come up with a solution, right. Once a solution is generated, the next part is to calculate its fitness function, right. So, the rest of the discussion we will be talking about how to determine the fitness function. So, to determine the fitness function, so we need to determine cost. Just to help you recollect basic mathematics, for a line connecting 2 points x1, y1, x2, y2, right. This is the equation of the line y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1. So, given any particular x, right, how do we calculate the value of y, right. So, we can rearrange this equation. So, we will keep y on the left hand side, we will take this y2 minus y1 to the right hand side, right. So, y2 minus y by x2 minus 1 into x minus x1, and this minus y1 we take it to the right hand side, that becomes y1. This is the equation that we will be using, right. So, in this case we do not have x1 y1 x2 y2, we have L, M, CL and Cm. So, this has to be lowercase x1 y1, right, this is lowercase x2 y2, right. So, if we substitute x1 is equal to L, x2 is equal to M, y1 is equal to CL, y2 is equal to Cm, we will get this equation. And similarly for the second part, right. So, this is for part A. So, if we get any production which is between L and M, we need to use this equation. If we get anything between M and H, we are not supposed to use this equation, right, because this equation is valid only between lower and medium level, L and M, right. So, between medium and high the equation is still same, the interpolation procedure is still same, right. So, instead of x1 we need to substitute M, instead of x2 we need to substitute H, instead of y1 Cm, and instead of y2 we need to use Ch. So, this is the equation to determine cost. So, now we know for any production between L and M how to calculate the cost, for any production between M and H we know how to calculate the production cost. So, this is just the production cost, these two equations are only for the production cost, right. So, similarly we can write equation for the investment cost also. So, this equation is still the same, right. So, here we were substituting CL Cm, right, for finding out the production cost. Here we need to substitute IL and IM, right. So, IL and IM are the investment cost. So, the total investment cost if the production is between lower and medium level can be calculated by this equation, and if the production is between medium and high level the investment cost has to be calculated using this equation, right. So, now we know how to calculate production cost and the investment cost, right. So, this is for a particular process, right. So, this is the same set of equation which we showed you in the previous slide, right, but there are different processes, right. Remember the table which we showed you at the very beginning, there are 54 processes, and for each process this L, M, H, CL, Cm, CH, IL, IM, IH can be unique, right. So, these values can be unique for each process. So, for the jth process these are the equations which we will be using for calculating the production cost. We will use equation 1 if it is between lower and medium level, the production is between lower and medium level, and we will use this equation 3 to calculate the investment cost. Remember the production can be either between low and medium or between medium and high, right. So, if it is between low and medium we will use equation 1 and 3, if it is between medium and high we will use equation 2 and 4. So, that completes the discussion on the cost determination. So, now let us discuss how to calculate the profit, right. So, let us assume that this is the data which is given, this table is the data which is given, right. So, we have been given 6 processes, we have been given production cost at different production levels, we have been given investment cost, we have been given how much raw material it requires for producing 1 unit quantity, we have also been given the selling price, right. So, let us say with this data we gave the lower bound to let us say TLBO 0, 0, 0, 0, 0, 0, right, lower bound is 0, upper bound is 20, 22, 20, 20, 25, 20, right. So, this is the upper bound, right. So, remember the lower bound is not this one, the lower bound is 0, right. So, if we give this to TLBO lower bound and upper bound, so let us assume TLBO returns back such a solution 6, 0, 10, 5, 20, 0. So, in this case we have chosen a feasible solution, right. So, if it is infeasible what we will do, we will come to that a little bit later, right. So, let us say we come up with this solution, right. So, 6 if we see it is greater than 5, right. So, this satisfies the domain hole constraint, 0, right, is less than 8, but it is 0, right. So, 0 is permissible. So, this is permissible and this is permissible, right. 10, right, the lower bound is 4 and we are say the upper bound is 20, right. So, and for 10 we can use this portion to calculate the production cost. So, 10 is fine, 5, right. So, the L is 2, right. So, anything above L and below H we can calculate cost. So, for this we will be able to calculate cost, and similarly for this we will be able to calculate cost because it lies over here. For each of this we need to calculate the production cost. If we decide to produce 6 units from process 1 for production cost, these are the two equations. This equation is valid between L and M, right, and this equation is valid between M and H. So, the amount that is produced is 6. In this equation we need to substitute 6 over here, right, and the low level is 5, the medium level is 10. So, wherever L is there we need to put 5, wherever M is there we need to put 10, right. For CL we need to substitute 10, and for CM we need to substitute 20, right. So, everything is known, so we will be able to calculate the cost. So, in this case the cost turns out to be 12. So, this is the production cost for producing 6 units from process 1. For process 2 the production is 0, so the production cost is 0. So, process 3, so process 3 we are producing 10 units, right. So, process 3 10 units, it is not between low and medium, it is between medium and high. We need to use the third equation, and instead of x we need to substitute whatever the algorithm has given. So, we need to substitute 10, right, and CM, CH, M and H you can look at the table and substitute. So, the cost would turn out to be 19, right. So, similarly the cost for these two can also be calculated, right. So, we have shown you for process 1 and process 3, you can calculate for process 4 and process 5. For process 2 and process 6 the production cost is 0, right. So, the summation of all this, right, comes out to be 74. So, that is the total production cost. So, if we decide to produce 6 units from process 1, 10 units from process 3, 5 units from process 4 and 20 units from process 5, the total production cost is 74. Right. So, similarly we can calculate the investment cost, right. So, this equation is for between L and M, right, and this equation it is between M and H, right. So, for the first and the third one, so first and the third one we have shown you the determination of cost. So, this is 52 and 66, this is 52 and this is 66. So, for the rest of the processes you can calculate, and if you sum these values, right, if you sum these values it will turn out to be 257. So, the production cost is 74, the investment cost is 257 if we choose to produce as per this plan. So, for raw material 1 this vector we have directly written over here, right, and this is the raw material 1 that is required for each of the process, right. So, here it requires 0.6, here it requires 0 into 0.5, so this is 0, so 10 into 0.4, 5 into 0.7, 20 into 0.9 and 0.8 into 0. So, this is the raw material required for each process. So, 3.6, 0, 4, 3.5, 18, 0, right. So, the total raw material required is 29.1. Similarly, you can calculate for raw material 2, it should work out to be 37.3, right. So, then we can calculate the revenue. So, again we have written this directly 6, 0, 10, 5, 20, 0, and this is the selling price per unit, right. So, 10, 0 into 10, 30 3 times, 30, 30, 30. So, this is the revenue earned by selling 6 units of whatever comes from process 1, right. For process 3 we are producing 10 units. So, each unit the selling price is 30. So, we get a revenue of 300, right, and so on, right. So, if we sum this up, right, this will come as 1110, that is what is given over here. So, then profit for each process we can calculate, right. So, here the production cost is 12, here revenue earned is 60. So, 60 minus 12. So, that is the profit from process 1 if we produce 6 units, right. So, similarly from process 2, process 3, process 4, 5 and 6 it can be calculated, right. So, here it will be 600 minus 27, right. So, that will be 573. So, this is the profit that is obtained from individual process, right, from process 1, process 2, process 3, process 4, process 5 and process 6, right. So, the total profit is the summation of all this, right. So, the summation of all this is 1036. So, remember investment cost does not play a direct role in the determination of profit, right. So, profit is selling price minus the production cost of all the process. So, this is what is going to give us profit, right. So, it is going to be a scalar value, and this investment cost is not used to calculate the profit. So, now let us consider what happens if we get a solution like this? This is x, right. So, TLBO gives 12, 20, 5, 4, 18, 0. So, the lower bound of all the processes are 0, the upper bound for all the processes are this one 20, 22, 20, 20, 25 and 20. So, that is the upper bound. So, now 12 if we see, it is greater than 5 and less than 20, right. So, it is in the valid region. 20 if we see, it is greater than 8 and less than 22. So, this is also in the valid region. 5 if we see, it is greater than 4, right, and it is less than 20. So, this is also in the valid region. 4 is greater than 2, right, and it is less than 20. So, this is also valid region. So, this 18 is greater than 10, but less than 25, again in the valid region, right. 0 is less than 3. So, that means this product is not produced. Only if it is produced, it has to be L or greater than L, right. If it is not produced, then it is 0. So, in this case, none of the 6 variables are violating their domain constraint. So, all variables are within their domain. So, the domain is 0, comma, Lj, Xj and Hj, right. So, it has to be either 0 or it has to be in this range, right. If it is greater than 0, so this is problematic, right. Xj is greater than 0, but less than Lj. So, if a solution falls in this range, right, then it is an infeasible solution. So, this is the domain constraint, right. So, solution if it is in this category and not in this category, right, then it is violating the domain constraint. So, in this case all the 6 variables are in their domains, right. So, there is no penalty. The penalty associated with each of them is 0. So, in domain constraint, the quantity that is produced by a process can be 0. So, 0 is permissible, but has to be greater than or equal to its low level production capacity, right. And if you have thoroughly understood meta heuristic techniques, you would also know that we will never get above H, because any solution that we get from the meta heuristic techniques is within the domain. It is going to be between 0 and H, right, but here we additionally want it to be either 0 or it has to be greater than L. So, whenever a variable satisfies this, right, that it is greater than 0 but less than L, right, then we will assign a penalty of 10 power 5. So, remember when we discussed constraint handling in the previous session, we said one of the approach was hard penalty. So, here we are using a hard penalty approach. No matter how much it violates, we are going to assign a penalty value, right, if it is not satisfying something that is required. So, here what we require is that Xj has to be either 0 or it has to be in this range, right. But if it happens to be greater than 0 and less than L, then we will assign a penalty of 10 power 5. So, this is for each variable. So, every variable that violates the domain constraint, we are going to assign a penalty of 10 power 5, and it is a hard penalty, right. So, in this case if you see, so none of these 6 variables fall under this category, right. So, wherever it is non-zero, 18, 4, 20, 12 fall under this category, that it is greater than L and less than or equal to H, right. So, that is why this solution does not incur any penalty. The penalty incurred by this variable is 0, the penalty incurred by this variable is 0, the penalty incurred by this variable is 0, and the penalty incurred by the rest of the 3 variable is also 0. So, the total penalty that is incurred is 0, because this solution does not violate the domain constraint. So, this is an example wherein some of the variables violate the domain constraint, right. So, for example, let us say we get such a solution from one of the meta heuristic techniques, right. So, 4. So, 4 is not allowed because it has to be either 0 or 5 or greater than 5, right. So, 4 is a problem. Similarly, 5, right. So, the low level is 8, right. So, it is less than 8, right. So, this is not permissible. So, similarly, if you see the rest of the 4 variables, each of the 4 variables violate the domain constraint. So, each variable incurs a penalty of 10 power 5. So, 10 power 5, 10 power 5, because here we have P domain. So, this is a name of a variable, right. So, P for penalty and domain for to indicate that it is a domain constraint. So, all these 6 variable incur a penalty of 10 power 5, right. So, the total penalty is 6 into 10 power 5. So, in this case if we see, right, so 9 is permissible, right, because 9 is here, 7 is not permissible because 8 is the minimum, right. So 8, this is permissible, right, minimum is 4, 0 is anyway permissible. So 6 is again not permissible, right, because it is less than 10, right, and 18 is permissible because it lies in this range, right. So the fifth variable and the second variable actually violate, right. So the second variable and the fifth variable actually violate the domain constraint, right. So this variable incurs a penalty of 10 power 5 and this variable incurs a penalty of 10 power 5. The total penalty for this solution, right, for violating the domain constraint is 2 into 10 power 5. Remember, there are multiple constraints. Right now we are only discussing about the domain constraint. So if a solution satisfies the domain constraint, no penalty is assigned, but if it violates, then for each variable that is violating the domain constraint, we assign a hard penalty of 10 power 5, right, and the total penalty for that particular solution is the summation of all the individual penalties. So that is how we are handling domain constraint, right. So now let us see how to calculate the production cost, right. So this we have discussed, these are the two equations which we had discussed, right. So if a production is permissible, so what do we mean by permissible? 0, right, and greater than or equal to L and less than or equal to H, right. So it can be here or it can be this 0, x cannot be greater than 0 and less than L, right. So this is not permissible. The algorithm does not ensure this, right. So the algorithm knows this as lower bound and this as the upper bound. So it can give any value between the lower and upper bound, right. So now if we get a solution over here, right, let us say lower bound is 10 and the algorithm is giving a value of 3, right. So then we do not know how to calculate the production cost, right. So production cost cannot be determined if production is not in the permissible range. Let us assume that this is the solution that we get from one of the meta heuristic techniques 9, 7, 8, 15, 6, 18, right. So some variables are not in the valid region, right. So 7 and 6 are not in the valid region. For process 2 minimum is 8, but what we have is 7, process 5 minimum is 10, what we have is 6, right. So these two variables are violating the domain constraint. So the production cost for these two variables cannot be calculated, right. So that is what is indicated, and for the rest of the 4 variables we have already discussed how to calculate the production cost, right. It is based on where it lies. One of this equation has to be used with the respective LMH and CLCMCH to calculate the production cost, right. So the production cost for producing 9 units from process 1 turns out to be 18, right. For process 3 to produce 8 units it turns out to be 16, for process 4 it is 28, and for process 6 it is 35, right. So the total production cost is 97, but the solution will have a penalty for violating the domain constraint. For a solution which does not satisfy the domain constraint, this is how we calculate the total production cost. If the solution is like this, let us say if the solution is 4, 5, 2, 1, 5, 2, this you can compare and you will be able to infer that all of these variables are actually violating the domain constraint, right. So if a variable is violating the domain constraint, as we just saw, we cannot calculate the production cost, right. Here the production cost cannot be calculated. So it will be assumed to be 0, but there would be a penalty of 6 into 10 power 5, because for each variable that is violating we put a penalty of 10 power 5, and here all the 6 variables are violating the domain constraint. So that is the discussion about production cost. Now let us look at investment cost and budget. This equation we have discussed previously, that if a production is between L and M, we use this equation, and if the production is between M and H, we use this equation to calculate the cost. This will tell us investment cost with respect to each process, right. So that has to be summed for all the process, right, and whatever investment cost we get for the entire production plant. Let us say for process 1 we require investment cost to be 20, for process 5 we require investment cost of 70, and for process 8 let us say we require investment cost of 90, then the total production cost for this is 180. That should be less than the available budget. This is an information which is available as to how much money is available to set up the plant. So the cost of whatever we decide to set up should be less than or equal to the amount of money that we have, right. So the amount of money B is given, right. So this is the total production cost, right. Let us say in this case 200 was available, right, and this cost comes out to be 180. So 180 is not greater than 200, right. So we have 200, we require only 180. So the penalty incurred is 0, right. Otherwise let us say if we had required let us say 240, so the penalty would be 200 minus 240 the whole square. So, that would be the penalty for investment cost. So, this P stands for penalty and the superscript I is to denote investment cost. So, we have penalty. So, if we violate domain constraint, we are going to incur penalty. If we violate the investment cost, we are again going to incur penalty. So, let us see an example, right. So, let us assume that the total amount of money that we have is 400 monetary units, and this is the production plan which is suggested by one of the meta heuristic techniques 12, 20, 5, 14, 18, 0, right. So, all of this satisfy the domain constraint, right. 0 is anyway permissible. The rest of the 5 processes have a production which is greater than their lower level. We can calculate the investment cost for each of the process. So, again we have shown you previously how to calculate investment cost. So, for example, for process 3 we are producing 5 units, right. So, process 3 5 is over here between 4 and 9. So, we need to take the equation which is valid for between L and M, right. So, we need to use this equation. Instead of x we need to substitute 5, instead of L we need to substitute 4, IM and IL are 65 and 55, right. M is 9 and L is 4, right. IL is again 55, right. So, if you compute this you can calculate the investment cost. So, similarly, depending upon which region the production lies, you can use one of this equation to calculate the production cost of all the other variables. So, if we sum this up, right. So, this is the investment cost for process 1, process 2, process 3, process 4, process 5 and process 6. So, the total investment cost which we require is the summation of this 323, right. So, we require 323, but what we have is 400, right. So, what we require is less than what is available, right. So, there is no penalty to be assigned. So, it falls in this category. So, no penalty to be assigned. So, let us consider a case wherein let us say this is the decision variable 20, 21, 20, 19, 23 and 20. Again in this case all of these have their production greater than L. Depending upon what is the production, we have to use one of this equation to calculate the investment cost, right. So, the investment cost turns out to be 70, 70, 76, 80, 78 and 76, and the total investment cost is 450, but what we have is 400. So, what we require is more than what we have, right. So, in this case this turns out to be 450, right, and this is 400, right. So, this solution falls under this equation, right. So, it will be 400 minus 450 the whole square, that is the penalty, right. So, 50 square 2500. So, this is the penalty due to the violation in investment cost, right. This is another example, right. In this example all the 6 variables actually violate the domain constraint, right. So, if you see 4, 5, 2, 1, 5, 2, it is actually less than these values, right. So, in this case the investment cost itself cannot be calculated. So, over here we have 2 variables which are not satisfying the domain constraint, right. So, for those 2 variables we cannot calculate the investment cost, right. For the rest of the 4 processes, right, you know how to calculate the investment cost, right. So, the total investment cost over here is 271, right. The amount that is available is 400, right. So, this condition is not satisfied for this solution. So, the penalty that is incurred for violating the investment cost is 0, because it is not violating the investment cost constraint. But this solution will nevertheless have a penalty of 2 into 10 power 5 due to violation in domain hole constraint. Now, let us look at the raw material constraint. So, let us assume that this is the solution that we get from the meta heuristic techniques, right. So, from process 1 we are producing 12, process 2 20, process 3 5, process 4 4, process 5 18 and process 6 0, right. And we know how much raw material is required for producing 1 unit from process 1. So, if we produce 1 unit from process 1, we require 2 units of raw material, right. If we produce 1 unit from process 2, we require 1.3 units. So, here we are producing 12 units, right. So, it will be 12 into 2, right, 20 into 1.3, 5 into 0.8, 4 into 1.5, 18 into 2.5 and 0 into 1. So, that is the raw material required for each of the process, right. So, the total amount of raw material that will be required is the summation of all of this, right. So, in this case it turns out to be 105. So, the amount of raw material that is available is 120 units. what we require if we decide to produce according to this solution, right, then we will require only 105 units, right. So, that lies over here. So, here K indicates the type of raw material, right. So, in this case for this example we have only one raw material. So, this is for K equal to 1. So, K is equal to just 1. So, wherever you have K you just need to put 1. So, PR of 1 is equal to R of 1 minus summation of what is over J, right. So, summation of Xj into Rmj. So, this has to be Rm, right. So, Rm is given, right, Xj is what we get from the algorithm, right. So, this sum across all the process, right, if we have J process, R is what is available, right. So, here we have 120. So, 120 is less than 105, right. So, this is not satisfied, 120 is not less than 105. So, it will fall in this category, right. So, 120 is greater than 105. So, the penalty incurred with respect to the raw material constraint is 0. So, no penalty is incurred. We require only 105 units, whereas what we have is 120 units. So, this is a case wherein we are violating the raw material constraint, right. So, if this is the solution, again 20 into 2 is 40, right, 16 into 1.5 will give us 24, right, and this 20 into 1 will be 20. For remaining 3 processes also you can calculate, right, and the total raw material that will be required is the summation of this, which it turns out to be 173 in this case. So, what we have is 120 and what we require is 173, right. What we have is 120, right, and this is less than what we require, right, 173. This is what is we require, this is the required amount and this is the available amount, right. So, in this case we need to calculate the penalty by what is available, which is 120, minus what is required, which is 173. So, 120 minus 173 the whole square. So, that turns out to be 2809. So, this is how we handle raw material constraint. So, similar to our previous discussion, if we get a solution which is actually violating the domain constraint itself. So, these 6 values are less than these 6 values and they are not 0, right. So, in this case we cannot calculate how much raw material is required. So, the raw material here we cannot say that it is 4 into 2 or 5 into 1.3, right. So, that is because this production itself is not permissible. So, if the production itself is not permissible, there is no point in calculating the raw material that is required. If a variable violates the domain constraint, so the raw material required is not to be computed. So, this is a case wherein 2 variables violate, right. So, we can calculate for 9, 10, 18, 18, right, because those are greater than this L values and they will be less than H also, right. But for the 7 and 6, so this is the 4th and the 5th one, right. So, 8 and 10 is the lower level, right. So, we can produce 8 and above 8 or we should not produce. So, 0 is permissible, right. So, for here the raw material consumption is for these 2 processes it is not calculated. For the rest of the 4 processes we calculate the raw material consumption, right, and the total raw material required is 71. What we have is 120, what is required is 71, right. So, obviously there won't be any penalty with respect to raw material. So, this we are repeating multiple times. Just because it does not incur raw material penalty does not mean the solution will not have penalty. It will have penalty with respect to the domain constraint, right, but with respect to raw material it does not have a penalty. Now, we have seen how to handle raw material constraint, we have seen how to handle the investment cost constraint and we have also seen how to handle the raw material constraint, right. So, now let us look at how to evaluate the profit, right. So, profit in this case let us assume that this is the solution that we get from let us say one of the meta heuristic techniques, right. So, 6, 4, 10, 5, 20 and 0. So, 0 is anyway permissible for any process. Let us compare the other ones. 6 which is okay, right. 4 is not permissible because the lower level is 8. So, 4 is not permissible. 10 is permissible, 5 is permissible, 20 is permissible, right. So, for whichever process satisfies the domain constraint, we can calculate the production cost, right. Remember those 2 equations, you need to see whether it is between L and M or M and H and use the appropriate equation and calculate the production cost, right. And we can also calculate the revenue, right. So, revenue in this case is 6 into 10, right. So, that is 60 right. So, the second variable itself is violating the domain constraint, right. So, we will not calculate production cost, we will not calculate revenue, and the profit from that is also not calculated, right. So, from process 3 the production is 10, right. So, and the selling price is 30, right. So, the revenue earned is 300, right. So, similarly 5 into 30 is 150, 20 into 30 is 600, 0 into whatever is the selling price will still give us 0, right. So, this is the revenue. So, the profit is revenue minus production cost. Remember, it is not the investment cost. Investment cost is one time cost which is required to establish the plant. Production cost is the recurring cost, right. So, profit can be calculated for each process: 300 minus 19 281, 150 minus 16 134, 600 minus 27 573, and this will be 0, right. So, the sum total of this is the total profit, right. So, right now what we have done is we have seen how to calculate profit for a feasible solution as well as an infeasible solution. We have seen how to calculate the penalty for a feasible solution as well as infeasible solution for all the three type of constraints, right. The domain constraint, the investment cost constraint, and the raw material constraint, right. So, right here when we are saying types of constraint, right. So, there are three types of constraint. That does not mean that we have only three constraints. So, for example, take this data, right. So, we have 6 processes, right. So, we will have 6 domain constraints. For each process we will have domain constraints. So, this is one type. So, let us say this is type 1, right. We will always have one investment cost as per the problem definition, irrespective of any number of process we will have only one investment cost constraint, right. So, this is type 2, and in this case we have 2 raw materials, raw material 1 and raw material 2, and if both are available in limited quantities, let us say this is available in 300 and this is available is only 100, right. So, if this is available in 300 and if this is available in 100, right, then we have 2 raw material constraints. So, this is a type 3 constraint, right. So, we will have a total of 9 constraints over here, right. So, if we have j processes, we are going to have j domain constraint, we are going to have one investment cost constraint, and if we have k raw materials which are available in limited quantities, we are going to have k raw material constraint, right. So, the total number of constraint is j plus k plus 1. This is the total number of constraint. The type of constraints are three types of constraint: domain constraint, investment cost constraint, and raw material constraint. Remember, as per the problem definition, we do not have any constraint on production cost. So, production cost is required to calculate the profit. So, now we know how to calculate objective function, how to calculate the violation with respect to each of the constraint, right. Remember, for production planning problem, what is to be returned is the fitness function, right, and not the objective function, right. So, objective function plus penalty is the fitness function for a minimization problem. Right now we have a maximization problem. So, we need to convert the maximization problem to a minimization problem and then add penalty to the objective function, so that we get fitness function, right. So, we know how to calculate profit. Since there is only one investment constraint cost, we have the penalty incurred due to violation in investment cost constraint. This is the sum total of all the penalties, that is the total penalty incurred for violating the domain constraints, right, for all the variables. And then we have k raw materials, right. We know how to calculate the penalty for every raw material, right. So, there will be k such terms. So, we need to sum this. So, this is one category of penalty, this is the second category of penalty, and investment cost we will have only one penalty if the solution violates the investment cost constraint. So, we will have only one value for violating the investment cost constraint, right. So, if we violate the investment cost constraint, there will be a penalty and it will be just a scalar value, right. So, there is no investment cost constraint on each process. The investment cost constraint is on the entire production plant. So, the total penalty is addition of all these penalties, right. So, we add all these penalties, so that is our total penalty, right. So, we know how to calculate profit, we know how to calculate penalties, right. So, this lambda is the penalty factor that we had discussed previously, right. So, this is for a maximization problem. So, if we were to solve a maximization problem, right, then our fitness function would be profit minus lambda into penalty, right. But since all the meta heuristic techniques which we discussed and which we coded were for minimization problems, right. So, the fitness function we need to multiply by minus, right. So, this profit becomes minus profit and this minus lambda p becomes plus lambda p, right. So, this is the fitness function value. So, we know how to calculate profit, we know how to calculate the individual penalties and hence the total penalties, and we can combine this. So, this is a consolidated picture of whatever we have discussed. So, let us assume this is the production plan given by one of the meta heuristic techniques. So, for process 1 we need to produce 20, process 2 we need to produce 21, similarly 3, 4, 5 and 6. Now, if we see 20 and compare with this data, this is not violating the domain hole constraint. Similarly, this is not violating the domain hole constraint. This violates the domain hole constraint. So, we have a penalty of 10 power 5. Right. Similarly, these 3 values do not violate their low level production, right. So, no penalty. So, this is the domain constraint, penalty incurred for domain constraint, right. For this production plan, you know how to calculate the investment cost. So, depending upon in which region it lies, you need to use the appropriate equation, right, and you will be able to calculate the investment cost. So, we have calculated the investment cost and given over here, right. So, this data plus whatever the equations which we have discussed for this production plan will lead to this investment cost, right. So, for here if we see the third process is violating the domain constraint, right. So, the investment cost what we were saying is not calculated, is considered to be 0, right. So, the total investment cost is 374 and the budget which is available. So, this is part of given data, right. So, what we require is 374 and what we have is 300, right. So, we require more than what we have, we will incur a penalty. So, that penalty will be 374 minus 300 the whole square, right. So, that will work out to be 5476, right. Similarly, for this production plan, the amount of raw material required for each process can be calculated as shown over here. So, the total amount of raw material 1 that is required is 72.5, the total amount of raw material 2 that is required is 109.6, right. So, what we have for raw material 1 is only 50 and what we require is 72.5, right. So, again we will incur a penalty which is 72.5 minus 50 the whole square, right. So, that will work out to be 506.25. Here we require 109.6, right, what we have is 120. So, what we require is less than what we have. So, the penalty is 0. Similarly, we can also calculate the profit for all the processes, right. We do not calculate the profit for the third process because the value of the decision variable is actually violating the domain constraint. So, whenever variable violated the domain constraint, we do not calculate the investment cost, the raw material required, and we do not calculate the profit, we take it to be 0. So, the total profit if you sum this up should come out to 2511, right. So, 2511 is the profit for this plan, but this plan is not feasible, right. It is violating the budget constraint, the raw material 1 constraint and the domain constraint for one of the variables, right. So, 10 power 5 is the penalty that we have over here, right. So, 10 power 5 plus this 5476 plus 506.25 plus 0, right. So, for this problem we have taken the lambda value to be 10 power 15, right. So, the fitness function will be minus profit, it is given over here. So, minus profit which is minus 2511 plus 10 power 15 into all these values, right. So, if you work it out, it will come to 1.06 into 10 power 20. So, here we have taken a value of lambda to be 10 power 15, right. So, just to make sure that no feasible solution gets lost to an infeasible solution. If you have understood constraint optimization, right, for a feasible solution this will work out to be 0, right, 0 penalty. So, this second part will not have any impact on the fitness function, right. The fitness function will be minus profit, right. So, here we have given a penalty of 10 power 5 for violating the domain hole constraint, right, and we have given 10 power 15 as a penalty factor, right. So, you can take different values and see what impact it has on the performance of the meta heuristic techniques, right. So, we leave this for you to calculate, right. So, this is the given data and the amount of budget which is available is 300, the amount of raw material 1 and raw material 2 which is available is 50, right. Assume the production plan to be 6, 10, 5, 20, 0, 0, right. So, there are 6 processes, so we have 6 variables and calculate what is the penalty incurred for domain hole, what is the penalty incurred for investment cost, what is the penalty incurred with respect to raw material 1 and raw material 2, what is the total penalty, right. So, total penalty will be the summation of this, right. you need to calculate what is the total production cost, what is the revenue, right. So, if this is A and if this is B, this profit would be B minus A, right. So, we leave it for you to calculate, right. So, since it is feasible solution, the penalty is 0, right. So, if you plug that into that fitness function equation, you will still get minus of profit. So, minus 839 is what you should get. Whereas this is an infeasible solution, right. So, one of this variable violates the domain constraint, that is why we are incurring this penalty. Similarly, there is a penalty associated with investment cost and raw material 2, no penalty is incurred for raw material 1, right. That is because whatever we require is less than or equal to 50, right. So, total penalty again should be the summation of this, right, and the production cost would turn out to be 128, the revenue is 1870 and the profit is 1742. If you calculate the fitness function, it should turn out to be this. So, this is an infeasible solution, this is a feasible solution, right. All the algorithms which we have are for minimization, right, and we have converted this problem also as a minimization problem. So, between these two solutions, if any of the meta heuristic techniques had to select a solution, it would select this one because it has a better fitness function, right. We are minimizing it, that you need to keep in mind. The problem is a maximization problem, but we converted into a minimization problem, right. So, this solution would be selected, right. So, this gives a consolidated picture, right. So, this meta heuristic technique, as we have seen multiple times, it will convey the decision variables to the optimization problem, and the optimization problem is supposed to send back the fitness function value. For this x, what is the fitness function? For this problem, to calculate the fitness function, we need to check for the violation in the domain constraint, right. If it is violating the domain constraint, we need to determine the penalty, else the penalty is 0. Then we need to calculate the amount of raw material that is required. The amount of raw material required is less than what we have, then no penalty is to be assigned, else we need to determine the amount of penalty. Similarly, we need to calculate the total investment cost which is required, right. So, if it is less than whatever we have, then there is no penalty, else we need to assign a penalty. So, once we have calculated all the penalty, we need to calculate the fitness function, and calculation of fitness function requires the objective function, right. For this problem, the objective function is profit. So, we need to calculate the profit. So, for calculating the profit, we again need the production cost, right. So, depending upon how much we are producing from each process, we need to calculate the production cost of each process and then sum it up. Similarly, we need to calculate the total revenue, and the difference between the revenue and the total production cost will give us the profit, right. Once we have profit, we can calculate the fitness function as shown earlier. So, over here we have just compiled all the equations, right. So, this figure is the same that we discussed previously, right. So, here we have just put all the equations together. So, this is how we assign penalty for violating the domain constraint. This is how we calculate the penalty for violation in raw materials. This is how we calculate the investment cost and then check for violation in the investment cost. This is how we calculate the production cost, right. So, once we calculate the production cost, the revenue earned is selling price into amount that is produced. Once we know the profit, we can use this fitness function equation to calculate the fitness function, right. So, the penalty, the value of P is nothing but summation of all the penalties, right. So, here we have taken lambda value to be 10 power 15, right, and here we took the penalty for violating the domain constraint as 10 power 5. So, the domain constraint we did not even have in this form, g of x is less than equal to 0, right. So, if you remember, when we were first talking about how to handle constraint using meta heuristic techniques, we had said that if a condition is not satisfied, you can assign penalty, right. It is not necessary that the condition should be of this form, g of x should be less than equal to 0. Here we had this condition that x is greater than 0, but less than equal to L, right. So, that is the power of meta heuristic techniques, right. So, if we are not able to pose the problem in the conventional format, minimize f of x subject to g of x is less than equal to 0, h of x is equal to 0 and x within lower and upper bounds, even if we are not able to pose our problem in that format, even then we can use meta heuristic techniques, right. Why we are able to use meta heuristic techniques even in that cases? In meta heuristic techniques, all that we require from the problem is the lower bounds, the upper bounds and a way to calculate the fitness function value, right. So, given a solution, what is the fitness function value? That is all that is required for meta heuristic techniques, right. So, if we are able to pose the constraint in this form, well and good, we can pose the constraint in this form and then use mathematical programming techniques as well as meta-heuristic techniques, right. But if we are not able to pose the constraints in conventional form, we can still use meta-heuristic techniques. With that, we will conclude this session. In the next session, we will implement this production planning problem using MATLAB, right, and then we will deploy one of the meta-heuristic techniques that we discussed to actually solve this problem. Thank you.